In this video, I will talk about the deflection of beams. For that, let us consider a cantilever beam like this of any cross-section area. Let us say this is the cantilever beam which is fixed at one end. Here we have x equals 0 and x is L here, that is L is the length of the cantilever beam. Let us say some load is acting at the end, which is P. Now, after application of load, the beam axis, which is initially straight like this, will bend, will take this kind of curve. Will take this kind of curve. So this one we are calling as the deflection, maximum deflection delta. Okay, basically this delta is a function of this magnitude of delta depends on the magnitude of the load we are applying, that is P, that is load, that is P, and it also depends on the length of the beam. So length of the beam, that is L, and the deflection depends on the material, which material it is made of. Material, weaker the material, higher the deflection of the beam. So this can be defined by the Young's modulus. More the Young's modulus, more the strength of the beam. And we have finally the cross section. This can be defined by the I, which is called the moment of inertia. Higher the moment of inertia, stronger the beam is and lesser the deflection is. So this delta is a function of P, that is load, and the length of the beam, and E, material of the beam, and the cross section of the beam. Let us see how to quantify this deflection of a beam. This delta can be obtained by two ways. One is double integration method, and the other one is moment area method. Moment area method. This double integration method is a lengthy one, and this cannot be used for the GATE exam or 1 mark or 2 mark questions. This is something like a shortcut method, and this one is lengthy method. Double integration method is lengthy method. So let us see both the methods, both double integration method and moment area method. First, let us talk about the double integration method. The same cantilever. Let us take the same example of this cantilever. Okay. This deflection curve is nothing but the y of x. Deflection is nothing but y of x. Basically this y is a function of x because this deflection is varying with respect to the distance from the fixed end. If we differentiate this function one time, that we will get the slope. Slope of the beam is nothing but the differentiation of the deflection curve. So it is dy by dx. Okay. For the cantilever beam, the slope here is 0. So at x equal to 0, dy by dx is 0. And also we have at x equal to L, we will have the maximum deflection. And the deflection also at x equal to 0, y is 0. That is, the deflection is 0. So at the fixed location, both deflection and slope both are 0. And if we differentiate this slope function one more time, we will get the curvature. So the curvature is equal to d square y by dx square. This curvature or radius of curvature, which can be called as 1 by r. The inverse of radius is called the radius of curvature. Okay. We know from the bending equation m by I equal to sigma by y is equal to E by r. Okay. From this equation we can write something like this: EI into this 1 by r, considering these two, is equal to m, right? So this EI into this 1 by r is nothing but d square y by dx square, which is equal to m, the bending moment. So this equation is called the governing equation for finding the deflection, because if we integrate this equation two times, we will get the y value, that is the deflection. So to get the deflection, we are integrating this equation two times, so we are calling this method as double integration method. So to find out the deflection in the cantilever beam, let us consider any section at a distance x from the fixed end. Okay. Now we want to find out the bending moment at this location. The governing equation for finding the deflection is EI d square y by dx square is equal to m, right, where m is the bending moment. So here in this case, at this location, the bending moment will be the load into the perpendicular distance. The distance here is L minus x, right? So the bending moment is equal to load into the perpendicular distance from the load to the point where you are finding the bending moment, that is here. So P into L minus x, capital L minus x. And since this is causing this bending moment is a hogging bending moment. Hogging bending moment is like this, which is considered to be negative, and sagging bending moment is the positive. So presently we have the negative bending moment here. so I'm including negative sign here. So our equation will become ei into d square y by dx square is equal to minus p into L minus x. If we integrate this equation once, we will get ei into dy by dx is equal to minus pl into x plus p into x square by 2 plus constant of integration, that is c1. After this, we know the conditions as at x equal to 0, at x equal to 0 dy by dx, that is slope is 0. The slope at this location is 0 because if you draw a tangent to the deflection curve that is horizontal for a cantilever beam, so dy by dx is 0. If we substitute these two values in the above equation, we will get dy by dx equal to 0 is equal to at x equal to 0, right? This one is 0, this one is 0, so we are getting c1 as 0. Okay, now our equation will become ei into dy by dx is equal to minus p into L into x plus p into x square by 2. So our slope equation will become dy by dx is equal to 1 by ei into px square by 2 minus pl into x. Okay, this is our slope equation. There is no need to remember this. If we want to find out the slope at this location, that is x equal to L, we just have to put L here. After that we will get the slope dy by dx is equal to 1 by ei into pl square by 2 minus pl square, which is nothing but pl square by 2ei, pl square by 2ei. It is better to remember this equation, this final result, that is the slope at the end of the cantilever beam, that is the maximum slope here, which is pl square by 2ei. It is better to remember this formula. If we integrate this slope equation one more time, we will get the deflection equation, that is y. Now we are integrating for the second time. Now if we integrate this, we will get y into 1 by ei into p x cube by 6 minus pl into x square by 2 plus constant. This is the constant of integration. So here also we can apply the boundary conditions. At x equal to 0, we have y equal to 0, that is deflection at this location is 0, right? Y value, the deflection here is 0, so our equation will become 0 equal to 1 by ei, this part is 0 minus 0 plus c1. From this we can write the constant c1 is also 0, right? So our deflection equation y is nothing but 1 by ei times px cubed by 6 minus pl into x square by 2. So to find out the deflection here, that is the maximum deflection here at the end of the beam, that is delta, right? So if we substitute x equal to L, we will get the deflection at the end of the beam, that is delta. Y is delta at x equal to L, y is delta, that is maximum. So 1 by ei, we are putting x equal to L, right? So it is PL cube by 6 minus PL cube by 2. This is nothing but 1 by EI times, this is PL cube by 3EI, PL cube by 3. So the maximum deflection at the end of the beam, the beam of the at the end of the cantilever beam is delta, which is given by 1 by ei times PL cube by 3. It is better to remember this equation also. See, this delta is a function of all these parameters: load, length, material with which it is made of, and the cross section of the beam I. So the final equation is, we can remember this equation like this: the deflection y is, or delta, maximum deflection y or delta, which is given by PL cube by 3ei, and the slope dy by dx at end is PL square by 2ei, p into L square by 2ei. This one we have seen earlier, and this equation is this one. It is better to remember these two. For a cantilever beam, the slope is PL square by 2ei and the deflection is PL cube by 3ei.